Hey there, folks. We are back, and I want to work some of the problems that we did in class today. There's out of 3.4. There's only we only ended up doing 4 problems. Although a couple of them were non-trivial, and I think we maybe learned some good lessons from the work we did. Let's take a look at 1 part A, which says, okay, suppose you got an integer a that can be written as 11q plus r for some integer q and r. Show that 10a equals 11q prime minus r for some q prime. Now what stays the same in this is the r, right? Whatever this r is for a, that's the r we're talking about right there, but the q changes. Okay? So let's take a look at this. And note what happens when we multiply it out. So 10a, this is 10 times 11q plus r. And the form, remember what we have in mind here is I'd like to have 11 times everything, except I'd like to have a minus r dangling around out there somewhere. So it makes sense to me to distribute this 10 through and then get this 11 on the outside. Okay. Also, I really want a minus r, and it'd be nice if I could tuck part of this into this 11 business, right? 11 times something business. So I think it's helpful to just draw upon the fact that 10 is 11 minus 1. Okay? So we've got the 11 times the 10q, and then we've got, distribute the r, we've got plus 11r, and then minus r. So again, I can get a common factor of 11 here, leaving us with 10q plus r minus r. Okay? So a few sentences, I think we've got it. I can tell you what q prime has to be. It has to be this right here. So since 10q plus r is an integer, then the statement holds. Okay. If you want to, you can just say then let q prime equal 10q plus r, which is an integer. There you go. You got it. Okay, that was the 1a problem. Now 1b asks us to be a bit more general. In fact, if you look at problem B, it's really well, let me do it the other way. If you're looking at 1b and you look back at 1a, you think, oh, well, 1a was a special case of this when m was equal to 1. Okay? We want to show that, and still we've got the condition on a, show that for integer m greater than or equal to 0, 10m times a equals 11q double prime plus negative 1 to the m times r. Okay. All right. So let's do that. Now we are looking at a statement that's going to be true for integer m 0 or greater. So since that is a countable set, it makes sense to me to perhaps use induction on this. So I would start out by saying something to the effect, note that 10 to the 0 times a is just a. And which is then 11q plus r. And over here, that 11q double prime plus negative 1 to the 0 r is 11q double prime plus r. Thus and so, basically I just need to let q double prime be q. Thus the statement holds. And we have completed the initial step. Okay. Now we're ready for the inductive step. We say, okay, fine. Let's say that this holds for some non-negative integer k. Assume that 10 to the k times a equals 11 times q double prime plus a negative 1 to the k r. Okay. And then what we'd like to do is consider 10 to the k plus 1 times a. So let's put this over here. And think about what we want to do. I want to draw back on my knowledge about 10 to the k, or not my knowledge, but my assumption on 10 to the k times a. So it's a pretty easy job to factor out a 10. Okay. And now this gives us 10 times the quantity, 11q double prime, plus negative 1 to the k times r. Alright? Now, what I would ultimately like to see happen is that I would like to see this, where I replace k with k plus 1, look like this, where I replace k with k plus 1, and yeah, perhaps I replace this with another integer, but it has this kind of format, right? Alright. So, I think I'm going to draw, well, I can certainly for this part just swap these factors, right? Times 10 to the q double prime. Okay. And then I've got plus 10 times a negative 1 to the k times r. And again, I think this is really going to draw upon the fact that to get an 11 here, I can take the 10 up to 11, but then I need to docket 1 to keep it equal. In other words, 11 is 10. I'm sorry, let me say it the right way. 10 is 11 minus 1. So 11 times this, I'll leave that alone. But here I've got 11 minus 1 times a negative 1 to the k times r. Alright? So I've got to take this business right here and distribute through the parentheses. So I get 11 times 10q double prime plus 11 times a negative 1 to the k times r. And then right here, so this is minus a negative 1 to the k times r. Well, this whole business right here, I could pull out a common 11 as a factor, 10q double prime plus -1 to the k times r. And then here I can make this a plus, because this is a plus, and just say, well, I got another power of a -1. So this is -1 to the k plus 1 times that r. So really I just need to point out that this little business right here is an integer. Then the statement holds. And the inductive step is complete. Therefore, the statement holds for integer m greater than or equal to 0. Okay? Not bad, not bad. Fairly educational proofs. Learned some really good tricks here, right? 1C asks what initially seems like kind of a tough question. Again, we've got this condition on A, and we've got a Q and R that go along with the A. And it says, all right, well, use what we just proved to verify, and I should probably keep that in front of me, to verify that for an integer m greater than or equal to 0, 10 to the m is just 11 times some integer plus a -1 to the m power. Okay. Now, on first glance at this, let me just kind of pop this back up. Okay. When we're proving this, there's an a here, and there's an r there. And so what appears to be happening here is you're somehow getting rid of the a there and the r there. And so it almost looks like a division problem, but the problem with that is that if you divide this by some of those numbers, you can't guarantee that it's still an integer, and these things have to be maintained as integers. But as you look more closely at this, you realize that, oh, what if a is 1? What happens? Okay, so here's my little proof. Note that a equals 1 can be written as 11 times 0 plus 1. Okay, I'll say this as neatly as possible. Okay, so a has the form 11q plus r with q equals 0 and r equal to 1. Okay? And I should say 1. Right? A is 1. Then, using our formula from 1D, we have, and let me just make sure I'm getting it right, we've got 10 to the m times a, which is 1, equals 11 times some integer plus a -1 to the m times r, but r is 1. Okay. then, and now notice that this is not a chain. I kind of harp on this a lot, but it's an important point. This is not a chain of equalities. This is an equation. You know, we've popped a value into something we proved was identically true. Okay? So now, just simplifying both sides, I have 10 to the m equals 11q double prime plus negative 1 to the m. And that is what we wanted to show. So I'm going to quit right there. Okay? All right. One more problem that we did today, and that was the one regarding palindromes. Show that if m, which is a natural number, is a palindrome with an even number of digits, then m is a multiple of 11. And what I would, Joseph actually went through and kind of gave the salient points to the proof of the divisibility test for 11, but we can just use the test. Okay. So what I would do is something like this. Let's actually write this number m out. Okay, so let m have the form. So here's what typically happens. You know, you got your d sub 0, digit 0 that goes in the 10 to the 0 place, and then digit 1, okay, dot, 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 and you get out here to the 10 to the kth location. But if this thing is 2k long, then the rest of it has to match up with this. So again, you repeat the d sub k, and then on down to d sub 1 and d sub 0. Okay, that makes m then a palindrome with an even number of digits. And again, I mentioned this in class, but that bracket notation we're looking at is overused dramatically because we use it for inner products in linear algebra. We use it for vectors in linear algebra. Gosh, I think it's used for some other stuff too, but I can't think of anything else off the top of my head. But here we're doing it without integers or anything like that. So what it means is, here are the digits in a number. Please do not multiply them together. Right? This doesn't mean d0 times d1 and on and on and on. Okay? Okay? So now let's take a look at the divisibility test for 11, which basically is this. You take the odd position numbers, the first one, the third one, the fifth one, so forth. Add those, and then the even position numbers, you subtract those. And then what happens is the test says that, okay, if you're adding the evens and then you're subtracting adding the odd spot places and then subtracting the even, whatever the number you get there, your big number m will be divisible by 11 if that sum and difference that we just calculated is divisible by 11. Okay? So I'll point out to you that if we go through here, and I'm going to start on the end. So this is d0 minus d1 plus, and I'll do a little dot, dot, dot in here. There's actually a d sub k minus 1 just to the left of this, right? And that would be let's see. yeah, I guess it doesn't really matter if that's a plus, minus, whatever it is. If k is an even number, it would be plus, and if not, it would be, we'll see what goes. Oh, the kth position, I could take the sign off this, so the kth, d sub, let me leave a little spot here, d sub k minus 1, okay, on my even ones, even index, I get a I guess it doesn't really matter. I'm trying to figure out how to be as general about this as possible. Oh, well, 1, 2. Yeah, I can just put the index up there, right? -1 to the 0. Yeah. 1 is -1 to the 1. Yeah, okay. So this is k minus 1. I got it. Sorry. It took me just a second to get that. For some reason, I wasn't seeing it. Okay. Plus then -1 to the k d sub k. All right. And then plus -1 to the k plus 1. But now we're getting to the k plus 1 position is actually d sub k. Has that digit in it, right? Plus -1 to k plus 2. But now this is d to the k minus 1, right? Okay. On and on and on and on. And so plus dot 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 plus, and now -1 to the total here is 2k minus 1. I'm sorry, total is 2k digits, right? So the next one, this is d1, and then I'm going to squeeze this in, plus -1 to the 2k d0. Okay, so I'm sorry that's sliding off the side there, but that was kind of a long thing to write out. Well, let's simplify a little bit. d0 here, and then out here, well, you can think of this as -1 squared, which is 1, to the k, which is 1. Okay. No, these signs are not right. Let me see here. The index, if I did this, would be 2k. No, that's right. I think my signs are off slightly here. Let me see. K plus 1, k plus 2. There's something not quite right. Let's see if we can find it here. Oh, I know exactly what it is. We started counting with 0, so there's actually 2k k plus 1 twice, so 2k plus 2. So this is 2k plus 1, and this is 2k plus 2. There we go. Now I'm back on the rail. 2k plus 1, right? K through 0 is k plus 1 positions. And then the whole thing would be 2 times the quantity k plus 1. So that's 2k plus 2. Here's 2k plus 2. Here's 2k plus 1. All right, now I'm ready. So I got this plus -1 to the, you factor 2 out of that, and k plus 1. Well, -1 squared is Gotta be careful here. I'm still not completely. It's not position number though, alright, because I had a 0 position. I'll get there. It's position number -1. So this is, even though it's position 2k plus 2, it's 2k plus 1. I'm sorry I fumbled that around so badly. Okay. To the 2k plus 1. Alright, the 2k business, that's going to be a 1, right? Because -1 squared is 1, raised to k is 1. But that's going to give us a negative. Okay, so I'm going to hold on to that for just a moment, but it will generate a negative. And then for d1, I've got minus d1, and then plus -1 to the 2k d1 dot dot dot. And I think I'm going to put this down here so I don't have to. Part of my problem was I was squeezing everything in like crazy there. I've got a -1 to the k minus 1 d to the k minus 1, and then out here I've got plus -1 to the 2k d1 oh wait, I'm looking wrong. K minus 1, excuse me, k minus 1, and this is k plus 2, excuse me. Okay. Sorry, I was looking at the wrong one. And then here's my 2d sub k. So plus -1 to the k d sub k plus -1 to the k plus 1, that's here, d sub k. Alright, so d0, and now this is minus d0, right? And then minus d1, so these guys are gone, right? d1 is minus d1, and then this is a plus d1 because it's an even exponent, plus dot dot dot. Here, let's pull out the dk minus 1 common factor and think about what we get. We get a -1 to the k minus 1 plus a -1 to the k plus 2. Well, without getting too fancy on this, whether this is even or odd, this is the opposite, right? So one of these is positive, one of them is negative. 0. And then plus d sub k. And here we've got -1 to the k plus -1 to k plus 1. So same argument, right? Even or odd, it doesn't matter. This one's the other one. And so one is 1 and one's a -1. They cancel each other out. Boop. So this equals 0. And I'm sorry I fumbled so badly with this. I had it straight in my head for a little while, and then for some reason it left me when I was writing it out. Well, 11 divides that, right? I'm sorry. Then 11 divides m, or to say it the way they said it, or m is a multiple of 11. Okay, Sorry I did such fumbling around on that one. A little bit of tracking indices. I promised to give a clean proof of that. I'm not sure it was that clean, but at least I did go through and explain everything and clean it up as I went. A little messy. All right. So we will pick up after that on Tuesday of next week. Also, probably tomorrow at some point, I will go ahead and tape a lecture for what we're moving to, which I believe is relations. I need to look ahead and see. But, okay, hope that helps, and I will see you Tuesday.